we can predict future trends, like how fast an outbreak could grow or how many people might be affected. It's much safer and faster to simulate strategies like vaccinations, quarantines, and mask wearing in a model than in real life to see what might work best. Why is this topic important? It helps us prepare. It helps us prepare for and respond to real-world health crisis. Governments and health organizations use simulation results to plan resources allocation, like hospitals, medicine, and vaccines. By understanding how disease move through populations, we can design better strategies to reduce infections, save lives, and minimize social and economic disruption. Several foundational models and studies have shaped how we simulate the spread of epidemics. The SIR model by Kermack and McKendrick in 1927 is a classic paper, introduced the susceptible, infected, recovered model, which mathematically describes how infectious disease spread in a closed population. It is the basis for many modern models. Agent-based modeling of epidemics by Eubank et al. In 2004 is a study applied agent-based models to simulate how individuals' behaviors affect disease spread within cities. It's highlighted the importance of social networks and individual actions in outbreak dynamics. Strategies for mitigating an influenza pandemic by Ferguson et al. In 2006 used simulations to show the impact of interventions on slowing pandemics, such as social distancing and school closures. It influenced public health responses globally during events like COVID-19. What is exactly an SIR model? Imagine we divide the population into three groups. Group S for susceptible, Group I for infected, and Group R for recovered. Differential equations are used to model how individuals move from being susceptible to infected, then to recovered over time. We assume people gain immunity after recovering. The SEIR model is an extension of the SIR model that adds an exposed group. People who are exposed have been infected but are not yet infectious, which is also known as the incubation period. This model is more realistic for disease that have a delay between infection and when symptoms appear. Instead of using equations, agent-based models simulate the actions and interactions of individual agents. Here, agent means people or households. Each agent behaves based on rules, so it allows complex, realistic patterns of disease spread to emerge. This model is especially useful for modeling social behavior, movement, and random interactions. What are the main findings from the previous studies? Classic compartmental models like SEIR have effectively captured general epidemic trends, such as infection peaks and thresholds for herd immunity. Agent-based models have shown how individual behavior and social networks impact the spread, especially in urban areas. Prior simulations have helped predict the outcomes of various intervention strategies. However, there are some gaps I would like to address. Many existing models assume uniform mixing of populations, which may oversimplify real-world interactions. Some models lack the adaptability to incorporate changing behaviors or policy shifts over time. Few basic models explore multiple scenarios side by side to compare the effectiveness of different control measures. The objective of my simulation is to model the spread of an infectious disease through a closed population using the SIR framework. By analyzing how varying parameters such as infection and recovery rates affect disease progression, the simulation aims to provide insight into how quickly an epidemic can spread, peak, and decline under different conditions. Here's a simple diagram that shows SIR and SEIR compartments visually. The system modeled is a closed population with a fixed number of individuals, where no births or migrations occur during the simulation. Also, there is no death unrelated to the disease. Each individual exists in one of three compartments. Susceptible is for individuals who have not yet contracted the disease and are at risk of infection. Infected is for individuals who are currently carrying and can transmit the disease. Recover is for individuals who have recovered and are assumed to be immune to reinfection. Other assumptions of the model include homogeneous mixing. Every individual has an equal chance of interacting with any other. No latency period, which means no exposed stage as in SEIR models. The simulation progresses in discrete time steps. At each step, susceptible individuals have a probability of being infected based on contact with infected individuals and the infection rate beta. Infected individuals move to the recovered compartment after a certain period, governed by the recovery rate gamma. The total population size N remains constant throughout the simulation. What parameters am I varying? Transmission rate or infection rate, beta, it controls how easily the disease spreads. Higher beta means faster, more widespread infection. We could vary beta from 0.1 to 1 in steps and observe peak infection time and height. Recovery rate gamma controls how quickly infected people recover. Higher gamma means shorter illness and lower peak. We could vary gamma to see how long the epidemic lasts and how many people get infected. Initial infected population, IO, we could start with a small percentage, say 1%, versus larger percentage, say 10%, and observe how outbreak timing and magnitude shift. We can imagine the small percentage as a scenario of early detection and the larger percentage as late detection. With population size N, we can try various values like 100, 500, or 1000. It helps identify scalability and stochastic effects in small populations. I conducted 60 simulations in total, exploring combinations of infection rate beta, recovery rate gamma, initial effective count IO, and population size N. You might be tired of me talking. Now let's go to Python and do something fun. We can simulate individuals as dots that bump into each other and spread the infection. Each individual is a colored dot. Blue is for susceptible, and red is for infected, and green is for recovered. And infection spreads when red dots get near blue dots. People move randomly inside the 2D box. In the end, everybody gets recovered. Here's another simulation visually shows the epidemic unfold day by day. Again, blue is for susceptible, red is for infected, green is for recovered. We can see the peak infection time is around 40 days, and the peak height is around 300 people. Now imagine we encounter a new disease that we know nothing about, and we want to simulate it. Would anyone like to give me an infection rate between 0.1 and 1?
0.4.
0.4, okay. Anyone else give me a recovery rate from between 0.05 and 0.5?
Let's do 0.5.
Point what?
Say everybody. 0.5. Let's say everybody recovers.
Okay. Population size?
10,000.
Sorry?
10,000.
10,000. Initial infected people?
8.
Okay. So let's run the simulation. Oh, this looks weird. There's something wrong here. Maybe the population is too large. Let's
How about 3,000 or 2,000? Yeah.
2,000. Yeah. No. Problem is not here. Must be the recovery rate. It can't be like a 0.5, I guess. Anyone?
0.25.
2.5. This sum looks better. Here's our simulation results for the new disease. We can see the peak infection time is around, still 40 days. And the peak height is oh no, the peak height is like 1,000. Let's compare different scenarios based on the results. High infection rate caused faster and larger outbreak, peaking earlier. Low infection rate led to slower spread, sometimes never reaching a true epidemic. Fast recovery flattens the infection curve. High initial infected accelerates the outbreak and leads to high peaks. In large populations, the curves are smoother and match theoretical expectations more closely. What did the simulation reveal? Epidemic dynamics are highly sensitive to infection rate. Even small increases in beta can dramatically raise peak infections and shorten the time to outbreak. Faster recovery flattens the curve and reduces total infections. Starting with more infected individuals leads to faster and more severe outbreaks. From our main findings, we know early intervention is crucial. Reducing beta from the infection spreads widely. Reducing beta before the infection spreads widely can prevent an epidemic altogether. Public health measures that Public health measures that increase recovery rate can faster testing. Public health measures that increase recovery rates like faster testing and treatment help contain the outbreak more than expected. How could the simulation be extended? Use SEIR models to add incubation compartments and immunity loss. Incorporate vaccination, quarantine, or intervention policies as time-dependent variables. We can also introduce spatial dynamics like cities or regions using grids or maps. Modeling epidemics helps us prepare, adapt, and potentially save lives before the next outbreak begins. Thank you.
Very nice. I like the way you presented your research instead of assuming people would understand that you had research. Very interesting topic. Any questions or comments for Song?
Can I ask you a question? Did you see my collab? Let me show it again. Did you see this? All of this? Okay.
I believe
That's
so.
that's what
Yeah.
that's what I was worried about.
Oh.
If no one sees, so I was just like,
Well, if you saw it, we saw it.
okay, good.
All right. Okay. All right. Any questions about this project? Seiki?
Not a question, so I would say like how someone presents it is like I think it's really closely to like a formal like research how they would present. Yeah, because
Yeah.
I heard about like an economic research as well before,
Right.
and that's how they present. Usually they use a really white out background and explain about different things and really professionally. And yeah, for this part I think it's really professional, and I really like the animations, like showing like how it moves like with the disease in Python that way. And I think he incorporates like HTML as well.
Thank you. Yeah, the slide style is like a markdown style.
Yeah.
Yeah.
But it worked. And it's an important topic and it's a serious topic. So you use serious slides. It worked. Okay. Anything else? Anyone have anything else for Songbai? Okay, thank you. Yes, I take a look at some of the comments in the chat. They're very, very positive. Alex, can you hear me? I know you mentioned before something
Yes.
about, do you
Yes,
want me
Professor.
we
Yeah.
have some time. I don't think we'll have time for both videos.
Yeah.
But how about if I play your video now? All right.
Yes. Yes, that's
And
perfect.
okay. So just to show everybody, we've got the discussion. I'm not requiring a discussion, but you can always post things here. I have two threads with the two people who made videos, or two groups that made videos. And if I did my job right, I hope to put the others up here too. If I didn't do my job right, I won't. Okay, so this is Alex. We'll go to the YouTube link.